lecture 24, and still continue with the symmetric functions for so whatever we can learn. There's no big target here. What we know so far. So there is m lambda. It's a linear basis for lambda k, and depending on whatever m it could be. And then there is the E1 to Ek. So this is for lambda partition of k, right? Then these form an algebraic basis. Which means everything is a polynomial in EIs. And we did 3-4 types of things. So Ek was elementary, symmetric function, and Hk was complete homogeneous. Symmetric functions, and then Pk was power symmetric. So these are the elementary ones, and in different contexts, different ones are used and they appear. So these are by no means the end of the world in symmetric functions. There are many bases, and depending on the context, different guys are used. Okay, so we had written m mu in terms of Ek first, and then we got some matrix and we inverted and we proved vice versa. We proved that Ek can be written, or E lambda can be written in terms of m mu. So let's do this explicitly now. So if we explicitly try writing E lambda in terms of m lambda. So let's do an example. So let's say we have E4, E2, E1, and we write in terms of m lambda. So what is this? This is x1, x2, x3, x4 plus similar terms times x1, x2 plus x2, x3 plus similar terms plus x1 plus x2. So first of all, n equal to 7 is enough. So if we write in n equal to 7, then we have written everything. So why? Because 4 plus 2 plus 1 is 7. So 7 is sort of the minimum number n, which will cover everything. For n equal to 8 and 9, you can just extend the same formula. So now what is the largest possible lambda? This is what we have. So we want to write it in terms of m lambda. So what is the largest possible lambda in this sum? So first of all, the maximum that x1 can go to is 3. Okay, one term from here, one term from here, one term from here. So this is impossible. Impossible in the sense that m lambda will be 0 here. Okay, and so x1 to the 3 is possible. And if that is the case, then what is the largest possible x2? So if x1 you're taking all the, so the maximum possible x2 will be 2 because it can only come from these two terms, right? And then what is, if that is the case, what is the largest possible x3? It will be 1 because this term will already be covered, and similarly x4 is the maximum possible. So this is the leading term. So we will have to have uh, basically m3 to 1 is the maximum, is the biggest term possible. So one way to picturize the products here is to uh, uh, take a partition of 7, so 4, then 2 and 1, and basically you can put numbers or these numerals in increasing order. So for example, you can put x1, x2, x3, x4 here. Let me make it bigger. Well, this will change the page, so I'll write it here. So you can put various xi's here. So let's say this is an example. I can put this. This is the highest possible term. And you multiply all of them together and you will get a term from the product. Okay. So is that clear that every term corresponds to a filling of this lambda 4, 3, 4 to 1, such that terms increase from left to right. So why are they distinct here? So I can just write 1, 2, 3, 4, 1, 2, and 1 instead of xi's, and this is legal too. 2, 3, 5, 7 is also legal. 1, 3 is legal. 7 is legal. So this is legal. Terms should strictly increase from left to right. That's all.
Oh, Professor,
Yeah.
why do we have the strictly increasing condition?
Huh?
Why do we have the strictly increasing condition?
Strictly increasing is because of the way E4 is defined. E4 is defined as xi1, xi2, xi3, xi4, where I1 is strictly less than I2 is less than I3. So this is just representing a possible product in this whole product.
Oh, right. Okay, makes sense.
So in this one, it's the top guy, and this one it's this guy, and so on. So one thing we know is that every term corresponds to some filling, such that no terms increase from left to right. And in that case, it's clear that ones can only come maximum 3 times. Now, suppose ones come 2 times, then how many times can 2 come? 2 can come then 3 times. If one is come twice, then two can come three times, and so on. You can keep arguing that. Uh, you know. So if anyway, so what I'm getting at over here is an intuition behind what are the terms which are possible. So what is um, uh, what are all the, so first of all, this guy M3211 is simply 3211. So if you have E lambda, then the highest term possible is M lambda prime, where lambda prime is the conjugate of lambda. So this argument you got, right? That if there are three here, if the maximum guy is here, that's the maximum x1s which can come. And if they have come, and what we want to do is we want to, okay, so say this side is some number I need, let's say C lambda mu and M mu. So I want to say this mu is less than lambda prime. So what does this less than mean? What does this less than mean? So the less than ordering is called the dominance or natural ordering. And suppose you are given, so definition, let lambda and mu be two partitions. I mean, typically of some number, right? And you pad zeros, and lambda is less than, mu is less than lambda if mu1 is less than equal to lambda 1, mu1 plus mu2 is less than equal to lambda 1 plus lambda 2. Let's just go back to our example. If I had only the 4 here, if I had two ones, then number of twos can be 3. And basically the point is that one has to come on the left. So that's why there are exactly 3 possible. And the way to capture it is to say that so this lambda 1 starts as this x1 raised per 2, x2 raised per 3. The way it captures it is that this 2 has to be less than equal to the first guy, and 2 plus 3 has to be less than equal to the sum of the first two terms. So on up till mu1 plus mu n is less than equal to. Okay, so if we do this, it's clear that if this ordering happens, it is clear that C lambda mu is bigger than 0 if mu is less than lambda prime. This is clear. And it equals the number of fillings with, with mu1, uh, mu1 x1s, mu2 x2s, and so on. So is that clear? So here, this is, if this is the dominance ordering, then this is true. So I don't know what should I call it, just a fact. If this is the natural or dominance So in remark is that in your mathematics study, sometimes if you get if when you get coefficients of something you're calculating are always bigger than zero, then we look for a combinatorial object that counts it. So here, this is the number of fillings, uh, uh, whichever is possible with. Well, actually, this is not quite right. Yeah, actually, that's right. So you want C mu uh, m. Where have I written it? Yeah, m mu. So you need exactly so many mu one x1s and mu two x2s and so on. Okay, so this finishes chapter 2. So there is a longer example you can see in chapter 2. So I just took out a piece of it just to make this point, but in this is example 2.7 in Egg's book for a detailed look at this. So we are done with chapter 2.
Oh, Professor.
Yeah.
So here we took that all fillings have to be kind of strictly increasing from left to right.
Yes.
Likewise, we could have also taken strictly decreasing, right? That wouldn't change anything because at the
Um,
end of the day, you are just taking permutations over everything.
yeah, I think so. I mean, you subtract 7, I mean 8 minus this, and then you'll get decreasing. So suppose you have uh, 1, 2, 3, 4, 1, 3, 5, and then you take 8 minus this. So you take 7, 6, 5, 4, and then 7, 4, and 3.
Okay, so
That's
the 7 5,
7, 5. So that's a one-to-one correspondence. So
right?
the
Makes sense.
the point is that remember we were taking a leading term with x1 biggest type of thing. So if we have put some kind of ordering, then we would like something less than this uh, should work and so on. So either one of these sides should fill up. So that's why we did this. But yeah, you're right. You can do it this way. So it's the same object actually. Okay, so let's see now chapter 3. Uh, there are some items which we would like to cover. Other items are basically elementary. Um, this thing. So one thing which I noticed that we didn't write down explicitly was that if you have hk of xn, then that can be written as hk of xn minus 1 plus xn of hk minus 1 of xn. And we had done a similar formula for ek. This we had done. And then this formula we are done. So this we are done. And then he has some more formulas on pk, which we hadn't done. So, but there's some another thing that I realized was that we made a sort of mistake. So in our previous thing, so pk was a power symmetric function, and I wrote pt as summation pk t raised per k. This was wrong. It should be pt equal to pk t raised per k minus 1, or k bigger than equal to 1. So go through and make the changes. And let me show you where the changes are. So this was the mistake. It should have been k equal to 1, this thing. And rest will work out magically actually. Rest will be fine. Because I mean, this was a mistake. We getting k equal to 0 would have given us n here and wouldn't have convergence. A lot of problems would have happened. So rest all is okay, except here maybe it's, yeah, this is k going from bigger than 1. This is also okay. Okay, so we'll get back to this formula shortly.
Professor,
Yeah.
the t to the power should still be t to the power k, right?
Huh?
The t ka power should still be t to the power k, right? Because when we consider the generating function का like sum, तो उसमें for each xi to the power k we are getting a t to the k का factor as well.
Yeah, that's okay, but somewhere this is fine somehow. So what happens over here is that you know, well, we can rework it out. I just work it out, just see how it changes. I mean, there have been some issues here because I was putting from j equal to 1 onwards. So when you take k equal to 1, then you get t raised plus 0.
And t0 का term will only be the coefficient 1.
Yeah, no,
Like when you sum it up, it will be n.
so maybe there's something wrong here. So we let's go over this again. So let's see this again today. So okay. So yeah, I think that's the mistake that I was making. Okay, so let's go back and so you know, delete the rest and we'll make changes. So let's look at this again. So P of t, let's see what it works out to, is k going from 1 pk t raised per k minus 1. So this is k going k bigger than equal to 1, and then pk is xi to the k. Right? And is for k minus 1. So now so let's see. Let's take an xi out, and then I'll get xi t to the k minus 1. And this one, okay, so this is the reason why. So this is xi over 1 minus xi t. And okay, now it's fine. So that was the problem over there. There was no xi there. So I don't know what we did, but anyway. So now we can take the we can think of it as d by dt of ht, right? Because ht was, so Ayush, you want to switch your mic,
Oh, yeah.
1 minus xit, right? Um, so yeah, so I think we log. So I took the log and whatever, then didn't take the multiplier. I mean, forgot the chain rule or something. Okay, anyway, so this is this, and then this is equal to h prime t divided by h of t. So now, so p of t is times h of t is equal to h prime of t, and now we can get some kind of let's see if we can get a formula. So this is pk t raised per k minus 1, k equal to 1 to infinity, times hk t raised per k, k going from 0 to infinity, and equal to k hk t raised per k minus 1. I mean, it could be 0 to infinity or 1 to infinity 2. And now what are we comparing? So, well, now it might be actually a good idea to write it as pk plus 1 tk hk tk, this guy, and then if you compare the coefficients of uh, what do you get? You get k going from 0 to n, pk plus 1, and h of n minus k. Is that right? Well, let's compare with the coefficients of n plus 1, is it? So this is the coefficient of n plus, so we compare coefficients of t raised per n plus 1 on both sides. From this side you get this, and from this side you get n plus 1 h of n plus 1. Okay, because this is k minus 1, so I mean, if you're taking t raised per n, okay, so it's t raised per n actually. So then if it's t raised per n, then this is, I'm still confused here. So you're taking the kth term and n minus kth. Yeah, so I think this should be fine. Let's see what I have in my notes. Yeah, this should be okay. So, well, I know the final answer, so I'll compare it when we reach there. So this is the formula, pk plus 1 h n minus k, and the formula is usually stated in terms of h n h n. So I'll get n minus 1 pk plus 1, and there is something else. There's a k here. No, that comes over here. Um, so h of n minus 1 minus k, and now you shift the index of k to 1 to n. So this is pk, h of n minus 1 minus k plus 1. So this gets cancelled. Okay, I think I've got the right answer. So this is a formula I mean, as a recurrence relation for finding pk in terms of nk. So this is uh, okay. Similarly, you have one for en. So okay, so the implications are both en and hn are polynomials in pk. This is the implication. So pk also forms an algebraic basis. Okay, and another interesting thing is, suppose we have a base field was complex numbers. We could take it q, and sometimes we don't even need to take a field. We just take z. So what our previous results showed was that everything in elementary symmetric function and homogeneous symmetric function is a basis over z. Z meaning it's a module, it's a ring. So integral coefficients. You can write anything with a polynomial and integral coefficient, but because there's an n here, you have to have you have to have q when it comes to p. So when you're writing Pn in terms of ease, you may you may need to divide by something, or vice versa if you're writing ens in terms of p's. No, this is always okay. If you're writing ens in terms of p's, then you may need a rational number here. Otherwise, even an integer will work. So this is a remark. Remember it. Okay. Now we need some other formulas. So we have pt times ht is equal to h prime t, and we recall that ht times e of minus t was 1. So what one does is we multiply both sides. So multiply both sides by e of minus t. So you get p of t, h of t, e of minus t is equal to h prime of t and e of minus t. And again, this is equal to 1. So you get pk t raised per k minus 1, k going from bigger than equal to 1 is equal to summation k hk t raised per k minus 1, k going from 1 onwards, and this is minus 1 raised per k ek t raised per k, k going from 0 to infinity. I keep getting confused between these Cauchy identities, so I always go from 0 to infinity. And I'll put a k plus 1 here. This guy here. And then then it's okay for me. I can take n going from 0 to infinity and k going from 0 to n, and this guy k plus 1, h k plus 1, and then minus 1 to the n minus k, e raised power n minus k. And now we compare coefficients of, well, we can do n plus 1 here. So we'll compare coefficients of t raised power n plus 1 on both sides. So you get en or n, uh, again, n minus 1. So you get en here, and here you get k going from 0 to n minus 1, k plus 1, hk plus 1, minus 1 raised power n minus k minus 1, e raised power n minus 1 minus k. And again, we can shift this to go from 1 to n, and then this k comes back to hk minus 1 n minus k e raised power n minus k. All right, so this is a formula which the book has. And similarly, En is equal to summation k going from 1 to n minus 1 raised power n minus k, k times ek h n minus k. So the book has a very elaborate proof. He counts actually and sees it, so it gives some intuition. See proposition 3.2. And then I have written a note for myself that formulas for hk in terms of pk, this will be in the final. Okay, and the rest of so I don't know when I'll be able to make the final. Right now I'm out of ideas even for calculus. So first I want to get that out of the way. So in another couple of days, and then tomorrow I have to give another talk which I haven't really prepared. So it might take a bit, but hopefully by Thursday or Friday for sure I should have. But meanwhile, you have, if you look through the list, through the notes, you will find one or two problems which I have mentioned. So rest of chapter 3 is a connection with the material we covered earlier. The, the Stirling numbers, etc. So the first half of the course. So you can look through that briefly. You probably. So it's nothing surprising. They take special cases of H's and E's and P's and get various kinds of special, binomial identities, Q binomial identities, so on and so forth. Okay, so we carry on to chapter 4, and these are called Schur functions or Schur polynomials. Okay, any questions so far?
No, Professor.
Okay, if you don't mind, I'll just go and grab my coffee. Just take 1 minute, please. Okay. So yeah, so this is where I wanted to reach actually, because this is the first non-trivial set of examples um, of uh, of symmetric functions, and some familiarity is good. So we do some exercises, examples. That's the purpose here. I don't know if I can get into anything very deep, but some things which everybody should know. At least we should know the definitions. So, in fact, there are two definitions, and we will cover both, but maybe may not show they are same. Okay. So, before that, I think we need to know a little bit about what are determinants. So, I'll just define. I don't know. Have you? Uh, you must have seen a definition of determinants, right? Have you? Do you know what determinants are?
Yes, Professor.
Okay, then maybe I'm just wasting your time. So it's a sum over permutations, and um, so okay. Have you seen this definition?
Professor, in our Algebra 1 course.
Huh?
In our Algebra 1 course, we did see it.
Okay, but not necessarily everybody has seen Algebra 1, is it?
I don't think Dhruva has.
Okay, fine. So good. Then I'm not wasting your time. Anyway, it's good to see these things again and again. So I have to tell you this. Uh, you know this story, even though it might be quite boring, but anyway. So we when I was really good at algebra, okay, extremely good at algebra, and then I went to IIT Delhi to do my masters, and there was this linear algebra professor, and he was the epitome of boredom according to me, because I thought linear algebra was such a nice and peaceful subject, and I knew it completely, and I don't know what he was doing. I just couldn't get it. And basically, what he was doing was he was taking this definition of the determinants and proving one after the other results of all kinds. That this is, if you take two columns equal to zero, then it will be zero, and so on. And it was really boring. And I was really, very, very unhappy. That was the first algebra course, the first and last, where I got a C. I mean, it was so bad, according to me. And then when I finished my PhD, or was finishing my PhD, I got into combinatorics, and all I see is that definition. So you never know. Sometimes so I did. I mean, I did go through those proofs because he was doing it in the class. So I sort of had a clear. I had an idea of what's going on. I just thought, it's just unnecessary. I thought everybody knows.
Professor, I don't
Huh?
think we have ever really used this definition. Like we know what this definition is, but we have never really
Oh,
worked with it.
the thing is that that guy. So I mean, I have two stories like this. One guy gave me C, another one gave me D. Both I learned whatever I learned from them. It has always been useful. So one should never judge a professor. I mean, at least I don't now judge a professor. I learned my lesson. So the D one was even worse. The D was numerical analysis, and I thought that come on, I don't want to do numerical analysis. It's pure mathematics. I mean, I do pure mathematics. I don't do numerical analysis. And then I was really bad at it, you know. And then one fine day, suddenly there was an exam and I knew nothing. I was going to get a zero. And then one senior told me that you remember one thing. So I said, okay, what? So he said that there is one conceptual idea in numerical analysis. And he explained what it was. And what it was that if you have two Lagrange interpolating polynomials, then they are identical. And the reason is that if you have two polynomials of degree n, both monic, then they have at most n roots. So if you subtract the two, and if they have, it's a degree n minus 1 polynomial. So if it has n roots, it is identically 0. So this I learned. I went there. There was one problem, and I got 3 out of 20. Okay, and I tell you, I'm not kidding you. This is a trick I have used a million times in my career. And as far as determinants goes, I mean, I'm not even going to say. I mean, my whole entire work. I mean, my best friend he's an expert in determinants. I'll mention his name. And there was a paper we did together where, he couldn't do something and I could do, because I said that, what is so difficult about determinants? So, I mean, he knows tricks he knows all the tricks there are in the world, and still he didn't know one, which led me to a research, paper with him. So, both these profs were I'm very thankful for them now. But of course, I won't meet them. And anyway, so this is only for Dhruva. What does this guy do? This picks one element from each row and column. So a different element. So what it does is it goes through the rows, and the first guy will pick something, then something, then something, then something, but it will never repeat because it's a permutation. So it picks a representative of each row and column, and then it multiplies it. So you get all possible terms here. You get all possible terms which you will get when you were, expanding determinant. You get all possible terms, and then what is the sign you attach to that term? So we had this cofactor, this, that nonsense. The sign is, we assign a sign of sigma, and the sign of sigma, or SGN of sigma. This is defined in two ways. It can be defined in two ways. So it's the number of transpositions um, in sigma. That means, I'll just tell you what that means also. And this is also the number of involutions in sigma. So remember, we did involutions earlier. So inversions, sorry. So I less than j, then sigma I is bigger than j. This is an inversion. So the total number of this. So this was in lecture 7. So let's just do one example to remind you what all this is. I mean, even though I've done these things, but it's always good for me to just work out one example, especially after you're doing it after some months or so. 7162534. So this is the one variable, a one line notation, and what this means is 1 goes to 7, 2 goes to 1, 6 goes to, sorry, 3 goes to 6, 4 goes to 2, 5 goes to 5, 6 goes to 3, 7 goes to 4. Okay, so we are counting, let's count the inversions. So the first guy, I mean, I less than j, all of these are inversions, right? Because this is bigger than all of these guys. So 2 let's look at this guy. This is yeah, again, I mean, 2 is 1, but it's less than all the other guys, so there are no inversions here. 3 is 6, it's bigger than this, and this, so it's got 4, 5, 6, 7, all are inversions. 4 is 2, again, it's smaller than all these, nothing here. 5 is bigger than 3 and 4, so yes. Then 6 is not an inversion, but 7, there is one inversion. So how many are there? Well, 7, there's nothing. I mean, so sorry, 7 can't have anything. There's no J. Nothing bigger than 7 here. So there's no inversion. So how many are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So the inversions of this sigma is 12. So the sign is basically minus 1 raised to 12. Now let's write it down as disjoint cycles. So disjoint cycles, you can write it as 1 goes to 7, 7 goes to 4, 4 goes to 2, 2 goes to 1. Okay, then the first guy who's not covered here is 3. So 3 goes to 6, 6 goes to 3, that's over. Then 4 is covered, 5 and 5, there is nothing there. So this is a single guy, and 6 is covered and 7 is covered. So uh, this is uh, this is as a sigma as a product of disjoint cycles. Okay. Now, when it's a p cycle, its sign is going to be p minus 1, or minus 1 raised to p minus, because you can write this as a transposition. So how you write it as a transposition? You write it as 1 2 times 1 4 times 1 7, and this is already a transposition, and this also you can write it as a transposition. 1 5 5 1, 1 5 1 5. So 5 goes to 1. So let's check. So 1 goes to 5, 5 goes to 1, 1 goes to 7, then 7 is fixed, so 1 goes to 7. Similarly, 2 goes to, go from this way, goes to 1. It's fine. 3 goes to 6, that's fine. 4 goes to 1, 1 goes to 2, so 4 goes to 2. 4 goes to 2. So this is how you write it. How many are there? 1, 2, 3, 4, 5, 6. So there are 6 cycles. So sign of sigma is the same as minus 1 raised per 6, which is over here, same as this. So these are two equivalent definitions. You can see these transpositions are counting somehow the inversions in some sense, because you're starting from the first guy and going up. Somewhere they're essentially the same. So I won't show they are the same, but in general, you should know that if it's a p cycle, the sign is minus 1 raised to p minus. So in my time, there was this book, which is still my favorite book. It's called Herstein. If you do problems 1 to 10 on page 80 to 81, then you will know, you'll have a very good sense of what permutations are. So these problems, if you can do, that's a good idea. I mean, Herstein, I mean, combinatorics is not taught before algebra, but a lot of algebraic arguments, the nice ones are combinatorial. So I learned a lot of combinatorics in Herstein. It wasn't surprising that I liked combinatorics because I liked Herstein. Okay. Anyway, I won't go through and bore you with what my linear algebra prof taught me. I'll just tell some facts about determinants, that interchanging one row uh, or column changes the sign. I mean, it's from this definition, it's almost obvious because you interchange one row or column, it means you're multiplying by a transposition here. So it changes the sign all the way through in some sense. So if you interchange the sign, then you're basically putting one additional transposition there, which is causing all kinds of stuff. And this implies that if two rows or columns are the same, then determinant is 0. So yeah, why is this? Why does this imply? Because interchanging changes sign. So you get a equal to minus a if they're the same. So that will imply, or dit a is equal to dit. So this is there, and this is a very useful thing to know about the determinant. And I mentioned my friend, he's an expert. So if you want to get a taste of what you can do with determinants, then you should. He has a paper. It's available for free online. It's called Advanced Determinant Calculus, ADC. In fact, there are two papers, ADC 1 and 2, and he was my postdoc supervisor essentially. Essentially, he was one of the main postdoc supervisors. We also collaborated on two papers, both on determinants, in fact. So we tried many things. I told him I want to do some combinatorics, and then the, he was doing little complicated stuff there. So then we finally did something on determinants, which happened exactly as I told you, in a coffee shop essentially. Um, he said he couldn't. He had some thing. He's got the formula, but he can't prove it. So then I said, how difficult could it be? You've got the formula, just try. Then he gave it to me, and I did it. So it was, simple essentially. But anyway, so here is a proposition. This you may see multiple times in multiple courses. But we'll cover it again even if you've seen it. So delta x, so now somehow I'm using x equal to xn equal to x1 to xn, is the determinant of xi raised power n minus j. So ij going from 1 to n, and this is equal to this product formula. Okay, so this determinant is essentially, so I is the row index, so x1, and then you go n minus 1, so first column, n minus 2, n minus 3, and so on up till 1, then x2 n minus 1, x2 n minus 2 up till 1. Similarly, there is xn n minus 1. Okay, so the proof is very easy. So have you seen this before? Have you guys seen it before?
I don't recall it off the top of my head, Professor.
Okay, well, then you haven't seen it. I mean, you would have seen it in 11th grade. In 11th grade, you had all these problems like things like this. x1, x1, x1.
Oh, Professor,
Yeah.
can you scroll up a bit, please? I couldn't follow what the proposition exactly was.
So you've seen this kind of determinant for sure. Is this good? Or you
Yes,
want to do
Professor.
more? Okay. All right. So the proof is as follows. So you would have seen such examples in high school. But first of all, it's a polynomial. It's a polynomial in x1, x2, xn. This whole thing, right? And it is a homogeneous polynomial because you're taking one from here, one from here, one from another row, and all that. So the degrees have all add up, and it's of degree n choose 2. 1 plus 2 up till n minus 1, which is n choose 2. Okay. And then we note that the determinant, if xi equal to xj, then two rows become equal and determinant is 0. So this means that xi minus xj divides this polynomial, and this means that xi minus xj, this product I less than j less than equal to n, divides delta. Okay, and because they don't divide each other, so I mean these don't divide each other, so they divide the whole, and each one divides this guy. So I mean they're sort of relatively prime, so the product divides it. So what does this mean? Now this guy itself, I less than j, is also a homogeneous polynomial. And what is the degree? Same, n choose 2. So this means that delta is equal to some constant times xi minus xj. So this has, this has got x1 minus x2, x1 minus x3, x1 minus, I should write with a different color. So this one has x1 minus x2 times x1 minus x3, so on up till x1 minus xn, right? Then x2 minus x3, so on up till x2 minus xn. So the polynomial, the total degree of the polynomial is going to be, pick this term, then this term, then this term. It'll again come to be n by 2, n choose 2. So then basically they are the same up to a constant, and now you compare the main term. The main term. What is the main term? Main term is this guy. Compare this diagonal term. x1 raised power n minus 1, x2 raised power n minus 2, x3 raised power n minus 3 till 1. This chap, and the coefficient is 1 here, and same thing here. Coefficient will be 1 here. So main term meaning you're multiplying this with this, all these guys, then this, all these guys, and then so on. Coefficient is 1 in delta and in this product. So this implies that C is equal to 1. That okay. All right. So any questions on this proof? Now, this determinant is very, very important even in algebraic number theory. All kinds of contexts you'll see this. All kinds of contexts, wherever linear algebra is used and you want to, do something about distinct roots or something like that, then this kind of guy shows up. Because you want to show it's distinct. So somehow this is non-zero. If you show, then it's all roots are, distinct, things like that. It shows up all over the place. Okay, so note this delta is anti-symmetric, which is to say if xi is replaced with xj, then you get then delta of x1 to x, well, I should write it. This is the ith place and this is the jth place. So if you interchange two xi's, then you get a minus sign outside. And this is because it's a determinant. So this is not symmetric, this is anti-symmetric. Okay, so then we consider this thing. We consider something very similar looking. dAx, which is defined as the determinant of xi to the aj, ij going from 1 to n. So the determinant of x1 raised power a1, x1 raised power a2, and so on. Similarly, and where x is now same thing as our xn earlier, and a is a partition, not a partition, sorry, a is a sequence a1, a2, a3, an bigger than, strictly bigger than, strictly bigger. So if their two are equal, then this will be zero. The determinant will be zero. So you might as well choose something which is strictly distinct. So distinct. So I should remark that if ai equal to aj, then dA would be zero. So we consider distinct sequences. Okay. So some properties. dAx is a homogeneous polynomial of degree summation ai. dAx is antisymmetric. Antisymmetric, again, same thing, means the same. If xi is equal to xj or I not equal to j, then this is zero. Okay. So main term is x1 raised per a1, x2 raised per a2, xn raised per an. So remember, our main term always was important, which was the highest of x's and highest of x2s and so on. And what 3 implies that dAx is divisible by delta x, which was our van der Waals determinant, right? So let uax be defined as dAx over delta x. This is a then uax is a symmetric polynomial of uh, degree summation ai minus n choose 2. So why is it symmetric? Because both these guys are which one I was at? Because both these chaps are antisymmetric, right? So if I replace xi by xj, both will give me a minus sign, and then so it's symmetric. This is wonderful. Okay, and then now mm, this is a these we took a1 bigger than a2, so on up till an. This is a partition of summation ai into distinct parts. But somehow we want to associate this kind of symmetric function with a partition. So what we do is let lambda, which is lambda 1 bigger than equal to lambda 2 bigger than lambda 3, so on up till lambda n be a partition. So whatever, I mean, you can pad it with zeros. Okay, we define a sequence ai a, which is a1 up till an, by this following. So a1 is equal to lambda 1 plus n minus 1, a2 is lambda 2 plus n minus 2, and so on. Ai is equal to lambda I plus n minus I, and an equal to lambda n, right? Then by making what we are doing, we are getting a distinct thing, because remember what we are adding is basically we are adding this 1 plus 2 plus 3, so on. So this is called the delta 1, 2, 3 up till n. This one is the prototypical, the smallest distinct part, and we are attaching uh, lambda to that. So whatever lambda was, we attach that. Even if some of them were zero, this has got exactly n parts. Okay, and they're all distinct. So a1 is bigger than a2 is bigger than so on an. At most, last one might be zero. So again, you can pad lambda by zeros and n. So you can put lambda I equal to 0 for I bigger than length of lambda to get this. Okay, this is a bijection between partitions of length less than equal to n with sequences like this, strictly decreasing sequences of length n. So, which is to say that you can, just do it, and now we come to the definition. let lambda be a partition. Let ai be equal to lambda I plus n minus I for I equal to 1 to n. So should function in n variables is defined as s lambda of x is equal to this ua of x, which is dA of x over delta of x, with a as of. And this is for length of lambda smaller than n. And so any questions? So this is our definition. Our definition is a ratio of two determinants. The determinants both look like Vandermonde, except here you have a1, a2, whatever. And these AIs are formed from the delta. So it's delta 1 from the lambdas. Lambda 1 plus, I mean, it's lambda 1 padded with this delta, this kind of guy, which makes it a distinct partition. So, for a partition of partition lambda of length less than equal to n, it's clear that this belongs to length of lambda of xn. X is equal to xn, or earlier n, right? And um, for any lambda, now following rule defines a symmetric function in infinitely many variables. So S lambda of, so we want for n large enough. So this is x lambda of x1 to xn for n bigger than length lambda, and 0 if n is less than length lambda. So if length of lambda is much bigger than n, then we just define it as 0, and in that case, then you get this symmetric function. And the third thing is that if n is uh, if L, there's something confusion here, n has to be bigger than. So yeah, length if n is less than equal to L lambda. So what does this mean? No, this has to be bigger than. The main term of S lambda x1 to xn is x1 to the lambda 1, x2 to the lambda 2, x of L lambda to the lambda of L lambda. So this you get by just dividing the two main terms. So the main terms on the top will be x to the a1, x2 to the a2, and then you divide it by n minus 1, x1 to the n minus 1, x2 to the n minus 2, and so on. So you get this. Okay, so I think 2 needs a little bit of proof. Um, 1 is okay, both are anti-symmetric. And 2 we'll just look at next time. 3 is divide main terms of both. I mean, this requires some argument that when n is less than, I mean, we would like that when you have n xn becoming equal to 0, then it gets back into a smaller sure function. That's the purpose of this too. Okay, any questions? Any queries?
So, Professor, the proof of two, will we be doing it next class? Or?
Yes, yes, yes.
Okay.
It requires some proof, a little bit. So next time we'll look at the combinatorial definition and do some examples, some more examples hopefully. And also, please try to come tomorrow for my talk if you're around, if you can. It's on one of Ramanujan's functions, Ramanujan's uh, theorems. So if you come, that'll be good. And next semester, by the way, we have tried to keep the uh, a fixed time for this math colloquium. So if you're this time the talks were really good. I mean, people really presented some things in a very elementary and nice way. So I at least like them, and I think it's a good idea for students to know about. I mean, this is a very limited universe. There's just 4 or 5 profs you have. That like very handful of courses. So one doesn't get to know about other things, what's happening around. So it's a good idea to go for these talks. So, but then you have to keep the time free. So we've kept the talk. We have fixed the talk timing at at on Tuesdays at 4:30 p.m. So, and we've made sure we are making sure that all the math faculty at least don't have courses at that time, and hopefully no TAs and TFs either. So now it's up to students. If you're interested, then you can block that time and take courses accordingly. And you can also push within computer science people and all. Uh, all right. So I will see you.